Okay, let us discuss about anharmonic oscillator today. Uh, so, for doing this problem, what we need to know is the uh, already known things about the harmonic oscillator. So, we have discussed in the previous course uh, how to solve the harmonic oscillator problem, and that we have already seen the energy equation and everything we know. So, yeah, so the non problem for us is, or the non-Hamiltonian of a harmonic oscillator H naught uh, is something like p square by 2m plus my potential, that is kx square, that is the harmonic oscillator potential. It's a kinetic energy term. That is a Hamiltonian that we know. Okay, now we are putting some additional sort of a change in this Hamiltonian. So our real problem is not this. Our real problem is a Hamiltonian of this kind, which is having exactly the same components, 2m plus half kx square. So the potential is slightly modified. So the potential is not only having this kx square term, it is having an additional x raised to 4 dependence. So this is a kind of a correction that we are putting into this problem. So I take constant, it's not really a constant. So it's having some unit here. So I'm not really bothering about the unit. You know that this is x square, x raised to 4. So obviously when you're adding along with the energy term, the c will be carrying some uh, units in such a way that the entire term will become an energy term, right? So what we have done is nothing but added a new component to this potential term. So yeah, that whatever factor which is coming, I'm not bothering about that. That is nothing but the c. Okay, so this is something that we have to find out. It is a problem that we are interested to solve, and I write it as equation number 1. Okay, so yeah, how do we do that? This kind of a problem, how can we do using our perturbation analysis? Okay, so the step is nothing but h. We can divide that h into two parts. It's not plus an HP component, HP. So that HP magnitude has to be compared to the H naught, it has to be a smaller quantity, and we usually put it along just like H naught plus some lambda multiplied with the H prime. So here I'm taking my lambda as 1, so that it's nothing but H prime for simplicity. So I know that this H prime here itself is a smaller quantity, and I don't want this quantity to be carried explicitly. Okay, so the correction that I am going to put is a is itself is a smaller correction, so that will taken care our condition for validity sort of. Okay, so how do we find out this? Let's find the first order energy correction. No? First order energy. First order energy correction. Okay, so we know how to find out the first order energy correction. It's nothing but En1 is equal to phi n hp phi n. This is the equation for first order energy correction. So hp here is nothing but h prime, and that is nothing but our c x raised to 4. So that is phi n x cap raised to 4 phi n. So this is our first order energy correction, and what I have to find out is h cap raised to 4 acting on the unperturbed states. Hmm? h cap raised to 4. H cap is nothing but our position operator. So we in the harmonic oscillator we have defined h cap uh, in terms of a cap and a dagger, like this, like h cross by 2m omega a plus a dagger. Okay, a plus this is something that we have defined previously, and I just modify a little bit of it to put the m omega factor in the form of k. So something that I know is k is equal to m omega square. So m omega is nothing but k by omega. Okay, so I can write this as h cross m omega substituting as k. So that will become 2k inside the root, uh, and whatever is coming here is nothing but omega, right? K by omega. Yeah, a plus a dagger. So this is our x prime. Now x cap. So what we need to find out is not just x cap raised to 4. X cap raised to 4 is nothing but it's fourth power, right? Okay, so if you substitute that value x cap raised to 4 inside this equation, we can write en1 equal to c is and h cross omega by 2k square will be coming outside, and what we will be having is a phi n and a plus a dagger whole raised to 4 phi n. Okay, in the case of harmonic oscillator, we always will not be putting this phi. We can just represent the state with n itself. That is much more convenient. So yeah, so what will happen now? So we have done actually a similar problem on your examination I have given. I think you may be knowing this to solve already. But anyway, we will discuss it now. Phi n, what I need to find out is a plus a dagger whole raised to 4 phi n. Now I need to write phi n. Okay, I'll just modify this a little bit. Phi n and a plus a dagger square and a plus a dagger square into n. Okay, so this is actually this phi n is an orthonormalist system. That is how we define it, and I can use the condition of completeness wherever. So yeah, I will put the completeness condition here so that I'll have some modification of the expression. So there are different ways of doing this. I'll do it in this way. So put the completeness condition inside. So one sigma factor will be there, which is running from m, and n will be there. A plus a dagger square is there, and the variable over which my state is changing is m. This is m, and the m will come here, and the operator next to it is a plus a dagger square n. Okay, so this is just a modified version of the same thing, but you can see here this is n an operator, m here, m an operator, and the operator is same, and you know that it's nothing but the complex conjugate. So you can take the nd term as the square of the same quantity. That is a square of a complex number will look like. Okay, so this is m a plus a dagger whole square n whole square. This is equal to the square of the entire term. Okay, so still I need to evaluate this term. What I need to evaluate is m. Okay, I'll do it. Okay, so yeah, before that I'll just expand this a plus a dagger square into a square plus a dagger square plus a dagger a plus a dagger. So we know another condition which is connected between a and a dagger is this is equal to 1. So that will give you a dagger minus a dagger a is equal to 1, or a dagger is equal to 1 plus a dagger a. 1 plus a dagger a. So just substitute their value here. We'll get a square plus a dagger square plus a dagger is equal to 1 plus a dagger a. So this will become 1 plus 2 a dagger a. Okay, it's a modified version of our operator. So that will give you this quantity substituting over there, sigma m. Okay, m a square plus a dagger square plus 1 plus 2 a dagger a 1 n whole square. So how do we find out this? Here you know this m is actually varying from all the possible values, from whatever, if it is starting from 0 0 to whatever is the dimension of the space that you have defined. So entire value it will be passing through, it will cover but this and all the states. So yeah, but all those terms will not be contributing to the summation, as you can see this. uh, why that is? Because let's see, any let's take m is equal to n. The moment m is equal to n, if there is no operator, okay, you know that that value is going to be 1 if it is a normalized system. If m is equal to 2 and this quantity is equal to 1, then you know that it's going to be 0. So that is because of the orthonormality condition. So since there is an operator here, depending upon that, the state will be changing. So A acting on n, you know what will happen to the state n? State n will be reduced by one level, right? And will change into n minus 1. A square acting on that will change 2 times. So this quantity is going to have, let's split the entire equation into different terms. Like we can divide it into 3 terms. First one is m a square n, that's what m a dagger square m, and m is 1 and 2 a dagger a we can take together because both of them are not changing the state, right? A dagger a is what it does, a change it into n minus 1 and a dagger will again bring back into the normal n state. So both are actually when m is equal to n. So you can put it together. So okay, let us do it. Okay, all the remaining values are going to be 0. So you need just have to take the values whenever n is equal to. This quantity is going to have any value. So that you know, whenever a square is acting, that m has to be n minus 2 a square n, right? Then only it will become n minus 2 square. So that is the first term which is contributing. And another term which is contributing is a dagger. So in that case, it has to be n plus 2. N plus 2 a dagger square, and you have n here, that's good. Okay. And another term, it has to be n. And 1 plus 2 divided a n and the square of it. That is the whole summation. So what these values are actually, so a is acting on n, produces n minus 2 and n minus 2, that is nothing but 1. What is the coefficient which is coming? The n value produced. This is nothing but a acting on n, it produces root n, and another a acting on n minus 1, it produces n minus 1, and the entire term square plus here a dagger acting on n produces root n plus 2, dagger acting on n plus 1 will produce root n plus 2 square plus 1 acting on into uh, 2 a dagger a. So a acting on that, it produces root n. On n minus 1, a dagger acting, it will produce again root n. And the 2 factors, the square of this term. Okay. So this will give you something like n into n minus 1 plus plus 1 plus 2 plus 2n plus 1 square. Yeah, 2n plus 1 square. And that is equal to 4n square, 4n square plus 4n plus 1. Here this term is n square plus 3n plus 2, n square minus n. Okay. So how many n square is there? 1, 2, 6n square. 6n square plus 3n, 4n, 7n minus 6n plus 2 and 1, 3. So this is actually the it corresponds to our n a plus a dagger square square over 4 n. Okay, so this is that quantity, and your en1 now will become en1 is c. What is the constant? H cross omega square by 2k, right? H cross omega square by 2k. H cross omega by 2k whole square into 6n square plus 6n plus 3. So this will become 2 square is this is 4k square. So you can just take a 6 from this outside. It will become 6c, and 1 2 will be cancelling, so it is 3c h cross omega square divided by 1 2 will be remaining, and k square 2k square will be there, and here square plus n plus 1 by 2. So this is the first order correction in our energy. Okay, so what about the energy equation with first order energy correction? So that is nothing but En0 plus En1, right? En0 is nothing but our non-harmonic oscillator equation, that is n plus half h cross omega plus. Now we are adding the first order correction to it, that is 3c by 2k square cross omega square into n square plus n plus 1 by 2. So this is the uh, correction in energy of uh, introducing a perturbation of the order x raised to 4. So this is how the energy of a state will be modified when you are introducing uh, perturbation like this. Okay, so that is all about the energy correction to the first order, and now we have to discuss the correction in the wave function to the first order. We'll see that in the next video.